Good morning. Thank you for coming to AtScale. How's everyone doing this morning? My colleague Peter Hoose and I are excited to welcome you to another edition of AtScale focused on systems and reliability. I remember just a year ago standing on this stage talking about how it is an exciting time for us to be in systems because AI is influencing systems just as surely as systems are influencing AI. A year later, we have all experienced the magic of AI, whether it is through coding or just getting help with our real-world work that we're doing. And yet, even with the frenzied progress that has happened, the future of AI products is yet to be written. In today's talk, I will cover some of the tremendous innovation that is happening in the AI software stack, and then Peter will talk about the underlying infrastructure innovation that powers all of this. Because everything is changing, whether it is the design for our data centers, the network itself, power management systems, cooling systems, it's all changing and changing rapidly. And we have to deliver on all of this while doing our most important job, which is serving the billions of people around the world who use our products every day. So first, I wanted to talk about how infrastructure is not just one of the things that we are building. It is the thing that is creating the future of AI. Because we are not going to be able to harness the potential of AI without building this infrastructure. But this is not one of those usual times when we build infra, because the future of these products is yet to be written. So to build, we have picked these three key principles. And throughout the talk, Peter and I will reference these multiple times. Let's go over these in a bit. So the first is optionality. Many of us here work in the bottom of the stack, and it's kind of difficult to work in the bottom of the stack when you don't quite know what the top of the stack is going to look like. But that is the challenge that we're faced with, and the more we design with optionality in mind, the faster we will be able to move. That brings me to the second principle, which is around time to market. As we can all tell, this is a race. The potential of AI is so tremendous that we are all racing to harness it. So time to market is critically important. And then last but not least is the obvious one, which is around innovation. The existing stack doesn't really work for generative AI, and there's a lot of work done to be able to evolve it. So now I'll talk about how we are applying these principles to a few areas. Starting with post-training and reinforcement learning, I'll talk a bit about distributed inference, and then a couple of exciting systems research problems. So let's get started. To start, I want to harken back for those of you, how many of you heard the talk from last year or was present here in this room? All right, some of you. Great. So a year ago, we were primarily focused on climbing to the moon of AI training. If you remember, at the time, I was talking about taking a single training job and running it on this super large cluster with hundreds and thousands of GPUs. But a lot has happened in the last 12 months. The first is that these models, this is semi-obvious, I suppose, in retrospect, as the models got more complex, they also got very large in size. And then serving these models became prohibitively expensive. So as an industry, whether you look at Meta with the Llama models, or at OpenAI, or Gemini from Google, all of us have been creating these distilled versions of these models that preserve a lot of the model quality, but are a lot less expensive to serve because they are smaller in size. The other big shift that has happened is on the AI algorithm side itself. Most of us in the industry have now moved away from these dense models to these sparse mixture of expert-style models. And just last week at LlamaCon, we were talking about how these MOE LLMs only need to activate a portion of the model's parameters in order to answer a particular query, the parameters that are relevant to that particular expert. This gives us a lot more flexibility at serving time and helps us reduce the cost of inference. But the most exciting thing that has happened is really not about the cost of the models and how we're going to serve them more effectively. The most exciting thing that has happened in the last several months is the birth of these reasoning models. These are the ones that have chain of thought, they can do agentic reasoning, and this is where reinforcement learning has come into play. And as systems people, this is exciting because this is a fundamentally different problem. For pre-training, the scale of pre-training is largely bound by the number of high-quality tokens that the LLM is being trained on. But reinforcement learning is a different kind of problem. It is a mostly unbounded search optimization problem, where the algorithm tries iteratively to find a near optimal solution without falling into overfitting. This opens up some exciting systems problems for people here to solve. So let's dig into this a little bit in depth. So even though this diagram might look like it has a lot of boxes and is complicated, but really there are two major parts of it. On the left-hand side, you see the generator, and on the right-hand side, you see the trainer. What's going on here is we take the pre-trained model, because this is the post-training step, and then we give the LLM a large number of different things to do. Then we look at the quality and accuracy of the response from the model, and then based on that, the rewards model gives it feedback, and we update the model weights as well as the generator. And then we repeat this in a loop many times with many different things that we want the LLM to be doing. So what are some of the exciting problems here? I'm going to talk about 3 of them. The first is about scaling this step. Like, scale is what we are all here today to talk about. And we are still in the early stages of mathematically figuring out how to scale this step of RL. And this is where optionality is important, because I think as an industry, we are still figuring out what percentage of GPU flops we're going to devote to pre-training versus to post-training. The second one that I want to touch on is around efficiency and efficiently using the GPUs. But this generator step and the trainer step are pretty different from each other. And in order to be really efficient, we want to find a way to batch and asynchronously update these model weights. But we cannot do that if we are going to lose model accuracy in the process. But if we can create some separation between the generator and the trainer, we will be able to unlock huge opportunities for efficiency. Last but not least, I want to talk about latency and reliability. The prompts that we give the LLM here are very diverse in nature. Some of them might be like adding 2 and 3 to make 5. Some others might include these agentic operations where you fire up a browser, go and complete a transaction, for example, on the internet. Or you use one of the coding tools, and then you're doing some code editing in an editor. So the question becomes, how do we do such a diverse set of things while still providing decent guarantees for latency and reliability? The last thing I wanted to touch on here is around performance of this RL step. This is largely bounded by the time it takes the generator to produce a response, which is mostly bounded by the inference system time, the inference computation time. As a result, you'll see there's a lot of excitement now about inference systems optimizations, some of which was inspired by the team at DeepSeek earlier this year. I also want to touch on some of the systems components that we've been building to support these agentic use cases. I want to touch on one example today, which is the virtual machine vending machine, VM. As the name suggests, this is a service that very quickly vends out lots of virtual machines to run code execution instances, so you can run code in a secure manner and then tear it down very quickly as well. This is something we built in a matter of months and launched into production earlier this year, and it has massive scalability. It has currently been able to run 250,000 of these code execution instances together, and I believe we have more than 40 billion plus code execution instances that have been executed since it was launched in January. I'll just pause and say, I'm proud that we are moving fast in the bottom of the stack because time to market is really important. So for those of you here who work in the lower layers of the stack, it is time for us to really embrace this spirit of moving fast because that's the only way we're going to be able to win in the era of GenAI. So I mentioned I was going to touch on distributed inference, and you're going to hear a lot more on this later today in a talk by Anka and Andre. But I wanted to mention the key things here. So as the models have gotten larger, one of the very practical constraints we ran into is that they no longer fit into the GPU memory of a single host. So now we've had to take these models, partition them into multiple pieces, and then have them on different hosts. Now, this immediately created a bunch of challenges for us. First, on the right-hand side is semi-obvious. Now, in order to respond to a particular query, we need to discover which model partition to route to and then route successfully there. But the biggest challenge for those of us working in the job scheduling layer is that we now have new placement constraints for inference. Because now these different tasks, they need to talk to each other, and they need to be connected via the GPU to GPU backend network. And this was not a requirement for inference when we were talking about these things a year ago. And this is where the lines between the inference workload and the training workload are starting to blur. And Peter Hoose is going to talk more about this shortly as well. So stay tuned for more on distributed inference later this afternoon. Now that I touched on some of the innovative work that's happening in the model lifecycle, I want to focus on just leave you with like 2 problem areas that we're working on at Meta. Would love to hear more from you all, what ideas you have in this space when we meet later this afternoon. The first is around reducing hallucinations, which is obviously one of the biggest problems the current generation LLMs have. And the second is around looking at the programming model and what we can do to work through its constraints. So hallucinations are a really hard problem. It's not like we've figured out the magic solution to them. But we do know that retrieval-augmented generation is one of the standard techniques that we've all been using in order to give the LLM some more information and come up with more accurate responses. Mostly what's happening here is you take the query, you represent it as a vector, then you go look up additional information from this external source, and then the LLM can compose what it has in its own memory, as well as from this external source, and hopefully provide a more accurate response. The reason this is exciting for like the database people in the room is because this problem lends itself well to information retrieval techniques. And for here, we are using vector DBs. Vector DBs, in addition to being able to do simple filter-based lexical searches, can also do searches like similarity searches, where you can find the k nearest neighbors. At Meta, we're pushing the boundaries with techniques like GraphRag and others in order to provide the right amount of personalized context to LLMs in a secure and privacy-safe way in order for these to produce more accurate responses. This work is pretty early, and as the team makes progress, you can expect to hear more about it. All right, now let's take a step back and talk a little bit about the programming model itself. Like the programming model for AI today comes from classic supercomputing. It's like single program, multiple data. If you think about the pre-training step today, that's what's going on. We have the same program. We have it on hundreds of thousands of GPUs. And then we execute it with different parts of the input data that we are training on. This model also has kind of this all or nothing fault tolerance model, right? We all sort of know this now, which is when one GPU host fails during the pre-training step, well, the entire pre-training operation grinds to a halt. This has been a source of so much frustration for all of us because now we have to restore from checkpoints, which is an expensive operation to do. And as we have larger and larger clusters, well, failure is no longer an exception. Failure is a norm. And we don't want to spend all these GPU cycles just restoring from checkpoints. So several of us in the industry have really been thinking about what we can do to not be stuck in this all-or-nothing model of SBMD. And one of the approaches we are considering is kind of flipping the programming model on its head and introducing what we call single controller. This will seem very familiar to people in distributed systems. The idea is you have centralized control, and then you operate on tensors, which are strewn across a very large number of devices. These could be across different geographic locations as well. As soon as we centralize control, expressing complex forms of parallelism becomes much more natural. So for example, for something like pipeline parallelism, you can now take a mesh of devices and use that to represent one pipeline stage. And then transferring data between these can be expressed in only a few lines of code. We also think that this can help with the fault tolerance model, because now each of these devices can keep track of a record of the history of commands that were executed. And when a failure happens and one GPU host is replaced by a new one, it can resume by executing those commands again. The big deal here, of course, is that it's a change in the programming model. So it would indeed be a big shift. And we're in the early days of looking at this. And as we make progress on building it out and putting it in production, we will be sure to share more with the community. A lot of what I talked about today was about the software stack, the different parts of the model lifecycle, and the exciting systems work happening there. But make no mistake, there is equally exciting work that's happening in the layer underneath, whether it's data center design, looking at our network, and also looking at electrical systems, managing power, managing cooling. And I'm really pumped to welcome my colleague, Peter Hoose, on stage to talk about the exciting work that's happening in that layer of the stack. Welcome, Peter.
Thank you, Surupa. You know, I can't help but admit I really kind of want to go full Benson Boone and try to do a front flip off the stage, but I've been advised against it, so I won't. You know, something that Surupa just said really stood out to me, and that's that we're changing every layer of the stack. And this is kind of a bold and profound statement. And it's not just Surupa saying this. In fact, just last week at LlamaCon, Satya Nadella, the CEO of Microsoft, said much the same thing. He said, with this kind of change and changes like this in the past with the movement to web, we have to go back and rethink and relitigate every layer of the stack. That's pretty bold. It's pretty profound, right? And this has some pretty significant implications on systems and reliability. And changes of this magnitude, although rare, have happened before. Today, many of us take for granted the thousands or even tens of thousands, if not millions of servers that make up the traditional hyperscaling fleet. It's abstracted away through cloud interfaces on AWS, GCP, and so on and so forth. But it wasn't always that way. In fact, not that long ago, relatively speaking, of course, ignoring the gray hair on my face, things were quite a bit different. You actually had a system that looked much more like this. You had 2 to 4 nodes connected together. They were often managed and controlled through closed and proprietary software systems. And this was built on top of really industrial-grade CPUs, memory, and hard drives. Right? That was kind of how you built it. For disaster recovery and reliability, you would deploy this in a hot standby configuration, one on the East Coast and one on the West Coast. And that was just kind of how things were done. That is until 2003-ish, and Google came along and said, maybe this status quo doesn't work anymore. Maybe we should do something different. And maybe instead of a few highly reliable, robust systems, we can deploy many thousands or even tens of thousands of systems built not on top of these kind of industrial components, but on commodity hardware, on PCs. Instead of closed software and systems, we can use open software like Linux and Apache and MySQL and so on. And this change was so profound that, in my opinion, it set off the last 20 years of innovation in systems and networking and reliability. You can go back and look at changes in DNS and TCP and HTTP and all of these things that were influenced by this. It was profound. And that's why today is so interesting, because as Surupa just described, we're in another period of profound change. We're at the peak of this next kind of innovation curve, this crazy kind of period of the last 2 to 3 years where everything is changing. But you know what? I don't think we're at the peak. In fact, I think we're just at the beginning of the next 20 years of innovation in systems and reliability and infrastructure. And that's why this is so exciting, because this is a rare generational shift. It's indeed profound, and we have to go back and rethink and relitigate everything from the bottom of the stack all the way to the top. Now, the cool thing is, all these challenges, they have one thing in common. And guess what? It's the title of this entire event, scale. Now, for context, scale. If you haven't been working in training, about 2 to 3 years ago, at least for us, the state of the art for a large training job was about 256 GPUs. At the time, this was massive. It was really hard to deal with. But today, that's kind of quaint. It's tiny. In fact, with Llama 3, we announced that we built 2 24,000 GPU clusters to train Llama 3. With Llama 4, just last year, around October, we announced that we had a single cluster with over 100,000 GPUs in it. This is massive. Now take a moment and think about that. 256 GPUs to 100,000 GPUs. That's a 38,000% increase in just over 2 years. How many things do you know that are changing on that scale at that speed? Nothing. And having lived through web and video and everything before, I can tell you that this is unique. It's rare. It's our opportunity. Now, we also know that 100,000 GPUs, that's not actually the end game. In fact, far from it. We've already announced that internally that we'll have over 1 million GPUs online by the end of the year. And with that kind of change and that kind of scale, a whole bunch of new challenges and a bunch of new problems come along with it. To walk through some of those, I'll start at the physical layer in our data centers. I'll move up from there and I'll talk about the servers, where the compute comes together and makes this all possible. And finally, I'll talk through training and inference, where the products are actually made and serve the end users and the things that they know and love. Let's start with the data centers. Data centers are actually kind of one of my favorite places in all of infrastructure, because it's where physics actually meets the software. And for the last decade or so, our strategy's been pretty consistent. We stamp out these regions, they're about 150 megawatts in size, and we deploy these all around the US and all around the world. Now, 150 megawatts, if you're not in this industry, it's like, what does that mean? It's actually pretty easy to understand. About 1 megawatt is roughly about 1,000 homes. So this facility is about 100,000 to 150,000 homes worth of power to run and operate it. It's pretty massive. And we've generally used this kind of one-size-fits-all, and it's worked great for us. But as we know that Surupa just mentioned, that we need to look for optionality, we need to optimize for time to market, and we need to innovate to meet the needs of tomorrow. So that's what we started to do. We looked at new options and new innovations that we could do. And one of these was Richland Parish, Louisiana. This is a new 2 gigawatt facility that's physically about the size of Manhattan. Now 2 gigawatts, that's just like incredibly large. How do you even reason about this? Does anyone know what this is? Not all at once. The Hoover Dam, good job. Yes, this is the Hoover Dam. The Hoover Dam, for context, is one of the largest hydroelectric facilities in the United States, if not the world at one point in time. And guess what its total output is? Yeah, that's right, you guessed it. It's about 2 gigawatts. However, on any given day, the average output of the Hoover Dam is actually closer to about 1 gigawatt. And what that means is we need at least 1, if not 2 Hoover Dams just to power that single region. That's incredible, but it's also not entirely sustainable. We had to innovate and we had to think about how we could solve this power problem at scale. So we started to look for new, clean, and renewable options to solve this, and to solve that, we came up with an RFP seeking 1 to 4 gigawatts of new nuclear power generation in the United States. But just as we build bigger, we also know that time to market is key, and we have to go faster. And to do that, we decided to think outside of the box. I just talked about how we made this transition from a few robust and reliable servers to many millions of unreliable systems and unreliable services. And we moved that reliability from something done at the hardware level to something managed in software. Maybe we can do the same thing with our data center regions. If we can build many more of these things much, much faster, we don't have a problem. But we didn't stop there, because we know that optionality is key too. And for the first time in our history, we've begun to deploy our production workloads on the cloud. Now, we've been using the cloud for many years for non-production workloads, but this is a first for us in putting production on there. And we did this our way, because as Surupa said, we have to get it out fast. And to do that, we took advantage of the cloud providers' physical infrastructure, and we overlaid on top of that our core systems, our operating systems, and management layers like Twine to make this easy for people to use. Now let's move a little bit up the stack and talk about the servers. Now, we just talked about how power hungry all these GPUs are, how we need to build all this nuclear energy and things to solve this. So we went back and said, what are the options we can do in our server fleet? Are there things where we can gain more efficiency, that we can reduce costs or reduce the power? Can we change these things? And we took a second look at our server layer and in our storage layer in specific. And we discovered that if we take another look at QLC SSDs, these actually offer us a nice middle ground between our typical high capacity but low throughput hard drives and our low capacity and high throughput TLC SSDs. And they give us that nice middle ground, but they do so at a much better price target. And more importantly, they significantly reduce the power involved. And that means all that power and all that capital that we save can be redirected to GPUs. But it wasn't just for GPUs. It turns out this benefits all of our fleet, because making things more efficient allows us to move faster, allows us to pack more servers in those data centers, and allows us to serve more end users. But it wasn't just the storage layer. We took another look at GPUs. Surupa described, as we get towards these 100,000 kind of in larger training sizes, that any time that job can stop, those GPUs can sit idle. And if you have 100,000 of these, or even 1 million of these sitting idle, that's just money that you're wasting. It's unacceptable. So we built new software systems to help us detect and analyze and find the best performing GPUs in the fleet. They can do this before we run the first training job. They can do this at any point in time when we stop the training job as well. In addition to that, we discovered that some of these GPUs have these issues that actually aren't typically detectable in normal hardware systems and our metrics. These are like silent data corruption errors. And we've built new algorithms that allow us to detect these, which means we can take those problematic GPUs out of the fleet before they cause problems. The job never stops, the job never fails. Now, moving up the stack and starting to talk a little bit more about training in detail, there's some really interesting challenges that come along here. And one of the most interesting to me, at least, was when we started to approach about 30,000 GPUs, we ran into a problem that I never expected and never had seen before. And that's that the power oscillation between the time that job starts and the time that job stops is pretty massive. It can be on the order of 10, if not 15 megawatts of power. Now, if you remember back to that data center example, that's like 10,000 to 15,000 houses going off and on just like that. And it's pretty easy to see that this can actually be a real challenge for the grid and utility providers like PG&E. They've built these systems to design and assume these kind of linear ramp ups and linear ramp downs, not instantaneous massive changes of 10 to 15,000 homes worth of power. This is incredible. It's insane, and it's a really hard problem to solve. Now, I don't know about you, but when I got my start in systems and networking, I never really thought I'd have to worry about grid reliability. But here we are, and I'm all here for it. It's actually fun and exciting and a hard and challenging problem to solve. Now, we've tackled this in a number of different ways. As Surupa mentioned, we've implemented faster restarts for our jobs. We've implemented faster checkpointing. We're also moving from SPMD to a single controller model. All of this adds up to something that actually smooths out these kind of peaks and valleys, because it's something that's actually more manageable at the utility level. And this actually works for us as well, because our systems are also not immune to this. These kind of large spikes and massive power shifts, they can actually implement or disrupt and take our data centers offline as well. So anything we can do to smooth out this curve is a big deal. It helps. Now, that was one of the problems with training. Another really interesting one as you start to scale up is historically it's kind of assumed that you have these homogeneous data centers, these homogeneous regions, and everything looks the same. And as Surupa described, you have this really low latency, high cross-sectional bandwidth between all of the nodes in the machine. They can all talk at full bandwidth. But we just talked about the 3 different options we have for data centers. And as we get to these million GPUs, they're obviously not going to be all in one building in the near term. They're going to be distributed throughout the world. Now this presents a really interesting and obvious challenge. And that's that latency increases as a result of the speed of light over fiber. And as any network person will tell you, you can't change the speed of light. You've tried. But actually, technically you could, because it's the speed of light in fiber. And if you could actually just do this over, like a pure vacuum, it actually can go quite a bit faster. So any of the network people in the room, please go ahead and figure that out. In the meantime, until we solve that problem, we have to innovate across the training space. We also have to tune our model architectures to handle these physical realities and these physical constraints, because all these different data centers have different reliability and different bandwidth constraints, and all of this needs to be abstracted away from the end users and products. And that's training. Now at the top of the stack is inference. And inference is actually really exciting because this is the first time all these products come together to actually deliver a product to the end user. And as Surupa just described, historically we had very different hardware platforms between training and inference. Training had those high-speed back-end networks built on Rocky and InfiniBand like I just described, but inference, most of the things ran on a single machine. A model would fit on a single GPU, if not a single server. Today, as those models get bigger, we know that we have to serve them across multiple machines. But it's not just model size, it's also latency. Imagine you're trying to interact with a real-time voice and chat service, and it takes not just seconds, but even minutes to respond to you. It becomes completely unusable at that point. We have to change something. And that's why we're blurring that line between inference and training and bringing that high-speed back-end network to inference as well. What that means is we can use these machines as a single unit together. But it's not, again, just for latency and not just for model size. This actually offers us plenty of other benefits. Because as we all know, users increase throughout the day. Or at least hopefully they do. That's the point of all these products, right? And as they increase, that load on inference where this is served actually increases as well. And if we can use that capacity from training and inference and use that and move it elastically over from training to inference, that means we can keep up with those latency guarantees. We can make sure we serve those users without interrupting them. It's awesome stuff. And this is actually a really great place to end. Because at the end of the day, all this innovation, it's really exciting, it's really cool, it's great, it's a ton of fun to work on as an engineer, but none of this actually matters if these products don't work. And for context, any given day, our products serve over 3.4 billion people every single day. Nothing matters if these products don't work. Nothing matters if those experiences don't work the way they expect. We have to make sure that reliability is paramount and that these things function and that we serve those end users. That's almost half the world's population on any given day. Now, if I can ask you just to remember 3 things from mine and Surupa's talk, the first is that nothing matters if we don't serve the users. The second is between the two of us, we share more problems than solutions. From reliability, data centers, servers, training, and inference, the future is still yet to be written. And the third is, we're at the start of a generational shift. We're not at the end. We have the next 20 years of innovation ahead of us. And that's why this is so exciting, and that's why today is so exciting. Because the solutions are the ideas that are here today in the room. And it's all of us together as peers and colleagues that are going to go ahead and solve these problems. And as a result of that, we don't just get to experience that future, we get to build it. And with that,
I hope you're all pumped. Thank you so much for coming today. Have a great AtScale.